A situation without gravity is obviously one in space. In order to achieve this, though, you have to go a long way out into space. Astronauts in orbit around the Earth still feel the force of gravity, even though they are floating. Astronauts on the Moon still feel gravity, just that of the Moon. It is impossible to remove yourself from the influence of gravity, as gravity is a force without limit. It is everywhere in the universe. Wherever you are, you'll feel the pull of gravity. Maybe only slightly, but you will still feel its pull. The best you can do is to equal the force of gravity with another force. The reason astronauts float in space isn't because there is no gravity. It is because they are constantly falling. Astronauts are just the same as parachutists, except the astronaut carries its air with it inside the ship, and the astronaut keeps on missing the Earth. What keeps an astronaut in space is their acceleration, the ship that the astronaut is in, and therefore they maintain a very high speed. It still falls to Earth at the rate you would expect. It is just that it is moving forward so fast the Earth drops away from it at the same rate it is falling to the Earth. The ship has a high acceleration and therefore a reaction force because the spaceship keeps changing direction in a circular orbit. However, discussion of objects in space is a little extraordinary. Very few people are ever likely to experience space for themselves, so instead we can have a situation where we mimic the floating feeling of space. An ice rink. An ice skater generates a cushion of water on which they float by applying a large pressure to the ice beneath their blades. This pressure lowers the temperature at which water turns solid, and so the ice is a liquid at the same temperature as the rest of the rink. The rest of the rink doesn't feel this great pressure, so remains as a solid. As soon as the pressure is released, the ice becomes solid again. The same is true of rocks or any material. On the surface of the Earth, a rock is very solid. If you take the same rock and place it at the bottom of a mountain, this rock exhibits liquid properties as it begins to buckle. Gravity is still opposed by reaction force from the ice, but now we have greatly reduced horizontal friction, and so can apply horizontal forces to demonstrate Newton's third law. Take two people on the ice. They are close to each other and of equal mass. One ice skater pushes the other. Both ice skaters move away from each other. The distances can be worked out using Newton's second law of momentum, but the third law principle is shown. The first person applied a force to the second person. This first force made the second person move away from the first person. The second person, in turn, automatically applied a reaction force to the first person as a consequence of being pushed. This second force pushed the first figure away from where they started. If Newton's third law were incorrect, then we would expect to see the person doing the pushing staying still, whilst the other person moved away. Without friction, it is obvious to see this doesn't happen. With friction, the situation occurs all the time, because the friction is adding an extra force. Because we see both people move, we know that the action force of the first person on the second, pushing them away, generated a reaction force on the first person of the same magnitude but opposite in direction to the force applied to them. How do we know that the forces are equal and opposite? Well, we know that they are in opposite directions, so skaters move in opposite directions to each other. If we measure the velocity of each person after moving away and know how long the person was pushing for, we could work out the size of the force applied. In reality, it is easier to see as the ice does supply a low amount of friction, but it's still enough to stop the skaters. If our people were exactly the same mass, then we would see that the distance each person travelled from their start point would be the same as each other. They would both have travelled the same distance from push to stop. This shows us that the force was equal in magnitude. Changing the masses of the people is calculable and understood because of Newton's second law. All that would happen here is the momentum would be distributed differently due to the mass of each skater being different. The more massive person would move less distance than the less massive person. The momentum of each skater would be conserved because the more massive person would have a lower velocity than the less massive person. This is how a rocket works. The rocket generates a large force against a huge mass, the Earth. It generates a very large velocity, escape velocity, which will be dealt with in later topics. It generates this large velocity in order to leave the pull of the Earth.